We talk so much about these huge AI models, achieving all these incredible things, but it kind of feels like we just assume that you need practically unlimited computing power to make any real progress.
Right, like it's a given.
And that makes you wonder, doesn't it? Is the future of really advanced AI only going to be in the hands of those with the biggest budgets?
It's a valid concern.
But today, we're going to explore a fascinating counterargument.
Oh, absolutely. This report you sent over detailing the work of the team behind the Wing series of models. It's really insightful.
Yeah,
What struck me is how they're deliberately pushing the limits of large language model training with, well, significant resource constraints.
right.
And that gets right to the heart of how we can make this powerful technology more accessible.
Exactly. We don't want to be stuck relying on super expensive hardware forever, right?
Not at all.
And that's what we're going to dig into today. This Ling technical report, it lays out their methods, and we're going to pull out the most groundbreaking stuff for you, the core innovations, the breakthroughs that let them achieve really efficient LLM training. And it's especially interesting when they're working with, less than state-of-the-art hardware.
Right.
Because this isn't just about being efficient for the sake of it. It's about who gets to be a part of shaping the next generation of AI.
Absolutely. And that leads us to something we're seeing more and more of these mixture of experts models,
Right. Well,
like DeepSeek, Quen, Minimax 01 in certain tasks. They're demonstrating performance that's even better than their denser counterparts.
okay, so Mo mixture of experts, just to give everyone listening a quick refresher.
Sure.
The idea here is that these models aren't one big solid thing.
Right.
They've got all these specialized experts inside, and the model figures out how to route different parts of a task to the expert that's best suited for it.
Exactly.
It's like having a whole team of specialists working together, right?
Yeah, a very well-coordinated team. And the report points out a big challenge with this approach.
Okay.
The amount of computational power you need to train these models is just enormous.
Yeah, makes sense.
Typically, you'd need the top-of-the-line AI accelerators like H100s, H800s, the kind.
Yeah.
And that, as they point out, creates a real barrier to. Not only are those resources ridiculously expensive, but they're also not available to everyone.
Right.
So it really limits who can even get involved in developing and researching these cutting-edge models.
That's a huge problem.
Yeah.
And this is where the Ling project's work becomes really important. Their goal is to create training strategies that work even when you have limits on resources and budget.
Right. Efficient LIM training.
And it goes deeper than just clever optimization. It's about making advanced AI development more inclusive.
It is. And to really get what they've accomplished, it helps to understand their computational setup. They've got this table 1, in the report.
Oh, yeah.
It lists all the different AI accelerator devices they used labeled A through E.
Okay.
And it shows their peak flops, memory capacity, and interestingly, what they call a fair cost per hour.
Cost, huh?
Yeah. And right away, you see the trade-off.
Hmm.
The most powerful accelerators, the ones everyone thinks you need for these models, they're the most expensive. And here's the kicker, they're the least available.
Oh, so even if you have the money, you might not even be able to get your hands on them.
That's right.
That's crazy.
Yeah. But and the less powerful accelerators, while they might not have the same raw power, are much more accessible, and they can be a lot more cost-effective per unit.
So right from the start, they're working with a realistic view of the hardware situation.
Exactly. They're not assuming everyone has unlimited resources.
So that leads to some serious technical challenges, right?
Definitely. Training across potentially less powerful and different kinds of hardware, even across multiple clusters,
Yeah.
it throws up a whole bunch of complex technical problems. The report highlights 3 key areas they focused on.
Okay, let's dive into the technical details. What were the main research problems they tackled?
Well, the first one was all about making things work across different clusters and devices.
Makes sense.
You see, when you're dealing with different hardware architectures like DSAs and GPGPUs,
Right.
even basic operations like how they handle computations and communications can be inconsistent.
Ah, so it's not as simple as just plugging things together.
No, not at all. And those little inconsistencies become much bigger problems when you're working with complex architectures like Mo.
Okay, why is that?
Well, certain operations that are crucial for Mo, things like group gem, permute, unpermute, all-to-all, and even how you do distributed training, like expert parallelism.
Right, so specific tasks that are essential for MOE.
Yes, these might not even exist on some platforms, or they might work differently. So a big part of their research was developing ways to make sure computations were consistent and portable across all this diverse hardware.
So essentially making sure the models can actually run on different systems without falling apart.
Exactly. And that meant working closely with hardware vendors, creating specialized debugging tools. It was a huge undertaking.
Wow. So it's a whole other layer of research just to get the basics working across these mixed environments.
Yeah, it's pretty intensive.
Okay, so that's cross-cluster, cross-device compatibility. What was the second challenge?
The second one was all about making sure the synchronization across clusters was reliable.
Okay, synchronization. So making sure all the different parts of the training process are in sync.
Exactly, because we're talking massive models, huge amounts of data, and frequent checkpointing.
Right.
The core research problem here was how to ensure that petabytes of data and these model checkpoints were being synchronized quickly and reliably across clusters that could be geographically separated.
So not only are you dealing with tons of data, but it's also spread out geographically, making it even harder to keep everything in sync.
It is, and they had to come up with really fast and robust mechanisms to manage all these training artifacts to make sure the data stayed consistent even if the network had hiccups or if there were hardware failures.
Right, because any little glitch could throw the whole thing off.
Abs-
Sounds like a huge distributed systems problem on top of all the AI research.
yeah, it's a whole other level of complexity.
Okay, so we've got compatibility and synchronization. What was the third big challenge?
The third one was all about optimizing the cost and performance.
Okay, so making sure they're getting the most bang for their buck, so to speak.
Right. It wasn't just about getting the model to train, it was about doing it efficiently with limited resources.
So being smart about how they use the available hardware.
Exactly. And that meant researching ways to optimize how hardware resources are allocated and scheduled, figuring out the best trade-offs between how efficiently they could compute things and how precise the calculations needed to be.
Finding that sweet spot.
Yeah. And fundamentally, it meant designing the model architectures themselves in a way that would get the best performance possible out of the computing power they had. They call it rational model design and scaling.
It makes sense. They had to be really strategic with their resources.
They did. So their research was really driven by these limitations of working with constrained resources.
Okay, so how did they go about tackling these challenges? What were some of their innovative strategies for optimization?
They took a pretty multifaceted approach. Their goal was to systematically balance resource cost and model performance. It involved several different areas, but let's start with how they optimized the model architecture and the training itself.
All right, sounds good. What were some of the key academic insights that guided their choices for the architecture and training methods?
One of the fundamental things they did was apply something called model architecture optimization, which was informed by scaling laws.
Okay, scaling laws, so how the models perform as they get bigger and are trained on more data.
Exactly. They incorporated research on how both dense and AOE models scale with increasing size and training data. This helped them pick model architectures that were naturally a better fit for the computational resources they had at hand.
So it's like they were making informed choices about the model design based on a theoretical understanding of how these models behave at scale.
Right, exactly. Instead of just trying things out and seeing what worked, they were using theoretical principles to guide their decisions.
That's a much more efficient approach.
It is, but then they had to figure out how to train these models across all this diverse hardware.
Right, because each piece of hardware might have its quirks.
It does. So they developed this unified framework called DL Rover.
DL Rover, okay.
It integrates multiple existing training frameworks. It's really innovative because it creates a system that can work across different hardware environments.
Ah, so it acts as a kind of common language for all these different types of hardware.
Precisely, it hides a lot of the complexity of the different frameworks and hardware underneath.
Makes things a lot easier for them.
It does, but then to really understand how things were performing on these different platforms, they needed a way to pinpoint any bottlenecks.
Bottlenecks, so places where the training process slows down.
Right, and for that, they came up with this lightweight debugging tool called Xputimer.
Xputimer, cool name.
Yeah, and it's really clever. They claim it can reduce memory usage by 90% during task performance analysis.
90%, that's huge. How does it work?
It has two main parts, this really lightweight selective tracing and then a sophisticated diagnostic engine.
Okay.
So the tracing part, it only monitors the really critical parts of the training process. It's not tracking everything, which keeps the other head down.
Ah, so it's like strategically choosing what to pay attention to.
Exactly. It does this by intercepting specific things like API calls at the Python level and even some operations at the C++ CUDA level.
Wow, getting down into the nitty-gritty.
Yeah, it's deep. It records things like timestamps and the layout of the kernel inputs, and it even uses data compression techniques to keep things compact.
Clever.
And then you've got the diagnostic engine.
Right.
It takes all this data and analyzes it in real time using multiple layers of analysis. It looks at the call stacks, does in-kernel tracing.
Wow, really digging deep.
It can pinpoint the root causes of any problems in the training process super quickly and accurately.
That selective tracing seems like a game changer.
Oh, it is. It lets them get really detailed performance data without overwhelming the system.
Very cool.
And then they built on that cross-platform capability to develop EDI, which stands for Elastic Distributed Training.
Eat it. Okay, another one for the glossary.
It's a platform-agnostic way of doing asynchronous training.
Asynchronous, so things aren't happening in lockstep.
That's right. And it's really a combination of techniques that, together, can reduce training time by up to 66.1%, they say.
Wow, over 2/3 faster. That's incredible.
It is. So there's layer-wise synchronization.
Mm.
This means that the model's parameters are synchronized layer by layer during the forward pass.
Okay.
That cuts down on the communication overhead and allows computation to happen at the same time using prefetching.
Makes sense.
Then they've got this new thing called a pseudo-gradient penalty.
Pseudo gradient penalty.
It's a way to handle those sudden jumps and loss that you get with diverse training data. It's also designed to improve the model's ability to generalize by taking advantage of the differences between the workers doing the training.
Okay, so it's using the variation in the training process to make the model more robust.
Exactly. It's got a few parts to it. One is anomaly elimination.
Right.
So if a worker's behaving strangely, its gradients are temporarily ignored.
Kind of like an outlier detection system.
Exactly. Then there's weighted averaging, where the contributions of each worker are weighted based on how reliable their gradients are.
Makes sense.
And finally, there's gradient clipping, which helps keep things stable.
Okay.
And lastly, EDIET uses time-based synchronization.
Time-based as opposed to what?
Well, instead of synchronizing after a fixed number of steps, it happens based on a time threshold.
Interesting.
This allows the faster nodes to do more updates locally before they have to synchronize, which really helps with the straggler problem.
Straggler problem, so some nodes taking much longer than others?
Right.
Wow, so EDE is really changing how they coordinate distributed training, making it much more efficient and resilient across these different systems?
It is. But they didn't stop there. They also worked on optimizing storage.
Storage, so how they're handling all that data.
Yeah, they used techniques like device multi-tenancy and Puster for high performance and adaptability across multiple clusters. Their research in this area led to a 50% reduction in time overhead for most scenarios.
That's significant.
And they made it even better with their own distributed file caching system called Pcache.
Pcache.
It cuts down on the number of data copies and uses metadata caching to make I/O faster, especially for checkpoints.
Okay, so they're really streamlining how the data is being accessed and stored.
They are. They even came up with a strategy for selecting workers to avoid overloading machines.
Smart.
And they worked with the Megatron framework to distribute the writing of checkpoints more efficiently, which significantly reduced latency and memory usage for those operations.
It's clear they've put a lot of effort into optimizing every part of the training pipeline, not just the model itself.
Absolutely. They looked at the whole picture.
So what other innovations did they come up with?
Well, another key area was improving how they handled anomalies during training.
Anomalies, so unexpected events or errors.
Right. They created this multi-level anomaly detection system that monitors the training process in real time.
Sounds important, especially with all these different hardware configurations.
Oh, it is. It can detect all sorts of things, from hardware failures to problems with loss divergence.
Okay.
And it can automatically trigger checkpoint recovery to minimize any interruptions in training.
So it's like a safety net for the training process.
It is. It makes long training runs on potentially less reliable hardware much more feasible.
It sounds like they're really taking a proactive approach to dealing with potential problems.
They are, and that's crucial for making these kind of distributed training work in practice.
Absolutely.
And then they didn't just focus on training, they also worked on making model evaluation more efficient.
Evaluations, so how they measure how well the models are performing.
Right, and that involved creating data sets specifically for evaluation, coming up with better prediction strategies, and developing optimized prompting templates.
So making sure they're testing the models in the most effective way possible.
Exactly. One of their insights was that the standard evaluation metrics for base models can be misleading, especially early in training. So they came up with ways to better assess the model's actual capabilities, even before it's fully developed its instruction following abilities. Okay. They created this offline inference framework called Flood.
Flood, okay.
It allows them to do really large-scale evaluations across clusters with very little deviation of results.
So they're getting more reliable and accurate evaluations.
Exactly. And to top it off, they developed a system that links the evaluation results back to specific parts of the training data.
Oh, wow.
That way, they can see exactly which data is helping or hindering the model's performance.
That's a great way to get targeted feedback and improve the training process.
It is. And all of this makes the development cycle much faster because they can iterate and improve things much more quickly.
Makes sense.
But they weren't done yet. They also made some advancements in how the model uses tools.
Tool use, so how the models can interact with external tools and data sources.
Right. They focused on creating high-quality data for tool use, using knowledge graph technology and generalized calling instructions.
Hmm.
And they also developed new methods for adaptive tool learning.
Okay, so the model can get better at using tools over time.
Exactly. They're using techniques like rejection sampling and error correction to refine how the model interacts with these external tools.
Very cool. It's like they're giving the models a way to learn and adapt their tool using skills.
That's right.
So after all these optimizations and innovations, they put it all together to create the Ling models, Ling Lite and Ling Plus.
Exactly. And these are open source MOE models specifically designed to showcase their resource-efficient approach to training.
Okay.
Ling Lite is the smaller one.
Hmm.
It's got 16.8 billion total parameters and 2.75 billion activation parameters.
Okay.
And then there's Ling Plus, which is significantly larger.
Right.
It has a whopping 290 billion total parameters and 28.8 billion activation parameters.
That's a big jump.
Yeah, it is. And they trained Ling Plus on a massive amount of data, 9 trillion tokens, across all 5 of those hardware configurations we talked about earlier.
That's impressive.
It is. And they reported some remarkable cost savings by training on less powerful hardware.
I remember you mentioned that earlier. What kind of savings are we talking about?
Well, their analysis showed that if you train 1 trillion tokens on a lower spec system, you can cut costs by almost 20% compared to using a high-performance device like their Device D.
20%, that's a significant amount, especially when you're talking about these large-scale training runs.
It is. And this finding is really important because it shows that you don't absolutely need expensive, top-of-the-line hardware to train these state-of-the-art MOE models.
This really changes how we think about developing advanced AI.
It does. It's not just about who has access to the biggest and most expensive supercomputers anymore.
It's a much more level playing field.
Right. And the report goes into detail about the specific architectural innovations they made in the Ling models that contribute to this efficiency and performance.
Okay, let's talk about those. What were some of the key architectural choices they made, and what was the academic reasoning behind them?
One of the interesting things they did was use fine-grained experts.
Fine-grained experts.
Yeah, so their research explored what happens when you increase the number of experts in the Mo layer, but make each expert smaller in size.
Okay.
It's like having more specialists, but each one is more focused on a narrower area of expertise.
So more experts, but with less individual capacity.
Right, and the total capacity of the Mo layer stays the same, but now you've got all these highly specialized experts.
So it's a trade-off between breadth and depth of expertise.
Exactly. The idea is that smaller, more specialized experts can become really good at what they do, leading to more efficient representation of knowledge.
So it's a move towards greater modularity and potentially more efficient use of resources.
Right. But they realize that if you only have these highly specialized experts, you might run into problems when the model encounters more general queries.
So the model might become too fragmented and not be able to handle tasks that require broader knowledge.
Exactly. So to address that, they added a shared expert.
A shared expert.
Yeah. This is an expert that's trained on all the data, no matter which expert is chosen for a particular task.
Okay.
It's like a generalist alongside all of the specialists.
I like that analogy.
Yeah, it works well. And this shared expert provides a foundation of general knowledge. It helps prevent the model from becoming too fragmented.
So it's a hybrid approach, balancing specialization with a core of general understanding.
It is. And they describe how the outputs of the specialized and shared experts are combined in equation 2 of the report.
Oh, cool.
Yeah, it's a neat bit of math.
Makes sense. So how do they decide which expert to use for a given task?
Well, to route the tokens to the right experts, they use a dropless routing strategy.
Dropless routing, what's that?
It ensures that every single piece of training data contributes to the learning process.
Okay.
No data is wasted.
That's efficient.
It is. And then, to make sure the training is efficient, they added a load balance loss and a router Z loss to the training objective.
Okay, what are those for?
They're designed to prevent the tokens from being distributed unevenly across the experts.
So it's about making sure all the experts are getting a fair share of the work.
Exactly. You don't want some experts getting overloaded while others they're doing nothing.
It's like a good project manager, making sure everyone on the team is contributing.
Precisely. And then they came up with this really clever mechanism to stabilize the training process, especially in those early stages when things are still a bit chaotic.
Okay, what is it?
It's called stochastic routing warm-up.
Stochastic routing warm-up.
Yeah, a bit of a mouthful. So instead of just relying on the alerted routing mechanism right away, they introduced some randomness into the process early on.
Randomness. So the tokens are being sent to different experts in a more random way.
Right. And that prevents the experts from visualizing too early in the training process.
I see.
It avoids situations where some experts get overwhelmed with data while others don't get enough, which can really mess things up.
Right.
As the training goes on, they gradually reduce the randomness and let the model rely more on the learned writing distribution.
So it's like easing the model into the process.
It is. It's a really clever way to make those early stages of mode training more stable. They describe this process in detail in equation 3.
Okay, cool.
And they also made this other change to improve stability. They call it norm head or normed LM head.
Norm head.
It's all about addressing the instability in the output norm of the language modeling head.
Okay.
They found that this norm could fluctuate a lot, especially when there were sudden jumps in the loss.
Right.
And those fluctuations could destabilize the training.
Makes sense.
So what they did was apply L2 normalization to the weight of the LM head before it's used for prediction.
Okay.
It's like putting a damper on those fluctuations. It helps to separate the direction of the output vectors from their magnitude, which makes the training process much more stable.
So it's another way of making the training process more robust and reliable.
Exactly. They give the mathematical formulation for norm head in equation 4.
Oh, cool.
But beyond these specific architectural innovations, they also did something really important from an academic perspective. They systematically analyzed the scaling laws for their Mo architecture.
Scaling laws. So how these models behave as they get bigger and are trained on more data.
Right. This is crucial for understanding how these models will perform in the future as we build even larger ones.
Makes sense.
And while there's been a lot of research on scaling laws for dense models, there hasn't been as much focus on Mo architectures.
That makes their work even more valuable.
It does. They looked at how their Mo architecture scales with things like batch size and learning rate, and how that affects the overall performance measured by validation laws.
So really getting into the nitty-gritty of how these models scale.
Exactly. And their findings were quite interesting.
Okay, what did they find?
Well, they found that the way batch size and learning rate scale for Mo-E models is very similar to how they scale for dense models.
So even though the architectures are different, the fundamental scaling behavior is similar.
Right. And their research suggests that the best values for those hyperparameters are mainly determined by the total amount of computing power you're using for training.
So the compute budget is the key factor.
Exactly. And that's true regardless of the specific details of the Mo architecture or how much weight you give to things like the balance loss and Z loss.
So that there's a kind of underlying universality to how these parameters should be tuned, even across different model types.
It seems that way. And they illustrate this finding in figure charge of the report.
Okay, cool.
But perhaps the most significant finding from their scaling analysis is related to the model's performance itself.
Okay, how so?
Well, figure 13 shows that their Mo architecture consistently gets better results, meaning lower training loss, than a comparable dense architecture where they're both trained with the same amount of computing power.
Wow, so the Mo architecture is more efficient at using the available resources.
It is. They calculated that it's about 3 times more efficient on average.
3 times? That's a huge difference.
It is. It means that their Mo architecture can achieve the same level of performance as a dense model, but using only about 1/3 of the computational resources.
That's a remarkable finding. It has big implications for how we think about cost effectiveness in large-scale AI development.
It does. And their research suggests that this efficiency advantage actually increases as you use more computing power.
So the bigger the model and more data you train on, the more the MOE architecture outperforms the dense architecture.
Exactly. So as we move towards even larger and more computationally demanding models, the benefits of their MOE design become even more pronounced. They found that at a compute budget of 1E24 FAPUs, the efficiency lever was over 3.5x.
That's incredible.
It is. It really underscores the potential of MOE architectures, especially their specific design, for the future of very large AI models.
And especially in situations where you might not have access to the most powerful hardware.
Absolutely. And the report also goes into detail about the lessons they learned during the development and training process.
Oh, that's great. Practical insights are always valuable.
They are. They talk about the real-world challenges they encountered and how they overcame them.
Okay, what were some of the key hurdles they had to clear?
One of the big ones was ensuring training stability, especially when they were moving training tasks between different AI accelerators.
Makes sense.
They ran into things like loss divergence, those sudden spikes in the loss, and imbalances in how the experts were being used.
Right.
So they had to figure out what was causing these instabilities and how to fix them.
What did they do about the loss spikes?
Well, for those, they implemented retry and skip mechanisms.
Okay.
And if the spikes kept happening, they'd adjust the learning rate dynamically.
So like a feedback mechanism to keep things under control.
Right. And figure 14 in the report shows how effective these strategies were.
Okay.
For the loss divergence problem, their research showed that using head norm and z-loss really helped to improve stability.
Hmm.
And to handle the expert load imbalances, they combined their spike mitigation techniques with the load balance loss and router z-loss we talked about earlier.
So it sounds like they had to really understand how these large-scale Mo models could go wrong during training.
They did. It was a lot of trial and error, but they figured out ways to make the training process much more robust.
Very impressive. What other challenges did they face?
Well, another big one was achieving cross-platform alignment.
Cross-platform alignment, so making sure the training process works the same way across all these different hardware setups.
Exactly. And it turned out to be a lot more complex than they initially thought.
Okay, what happened?
At first, they just focused on making sure the basic computational operations worked the same way on each platform.
Right, the fundamental building blocks.
But they quickly realized that wasn't enough.
Why not?
Because when they tried migrating training runs between platforms, they saw significant differences in how the loss converged.
Ah, so even though the individual operations were working correctly, the overall training process was behaving differently.
Exactly. So they shifted their focus to making sure everything was aligned at the framework level.
Okay.
They wanted to ensure that the forward and backward passes for all the key modules, the attention mechanisms, MLPs, the router, were consistent across platforms.
Right, so every part of the training process had to be in sync.
It did, and they had to address things like precision errors caused by differences in floating point arithmetic between the platforms.
Right, because those tiny differences can add up over time.
They can, and they also had to deal with discrepancies in how tensor parallelism and auxiliary loss calculations were handled.
Wow, so they had to account for all those little details.
They did, and Figure 20 in the report shows their debugging process and how they eventually managed to align the loss curves across the different hardware platforms.
That's amazing.
Their work really highlights how important it is to do end-to-end validation when you're training in these mixed hardware environments.
It's not enough to just make sure the individual pieces work. You have to make sure the whole system is working together harmoniously.
Exactly.
So after all that work on training and optimization, they finally got to evaluate the Ling models.
They did, and they did it in a really comprehensive way.
Okay, how so?
Well, they tested the models on multilingual benchmarks in English, Chinese, math, and code.
So really putting them through the paces across different domains.
They were, and they evaluated both the base models and the fine-tuned versions that are designed for instruction following.
Right, because the base models are more general purpose, while the fine-tuned ones are specialized for specific tasks.
Exactly, and they didn't just use standard evaluation methods. They actually spent a lot of time refining the methodologies themselves.
Oh, that's interesting. Why did they do that?
Well, they realized that the typical metrics, like perplexity and generation-based scores, could sometimes give. Whoa, did someone just break the fourth wall? Let's hear it.
Oh, absolutely. Thanks for letting us know. We can definitely keep going.
Yeah, no problem at all. Where were we?
We were just getting into how the team evaluated the Ling models.
Right. And as I was saying, they realized that the typical evaluation metrics for base models can sometimes be misleading.
Why is that?
Well, especially in the early stages of training, before the model has really developed its ability to follow instructions.
So the usual tests might not accurately reflect the underlying capabilities.
Exactly. So they optimized the prediction target in perplexity-based evaluation.
Okay, how did they do that?
Instead of just predicting the next word from a limited set of options, they changed it to predicting the entire content of the option.
Interesting. So it's a more fine-grained way of seeing what the model understands?
Precisely. This gave them a much better signal of the model's progress throughout the pre-training process.
That makes sense. And what about the generation-based evaluations?
For those, they focused on optimizing the prompt templates.
How so?
They added things like few-shot examples to implicitly guide the model's reasoning and make sure it stuck to the required format.
So giving the model a little extra help to understand what's expected.
Exactly. They also configured stopping criteria to make sure the reasoning process concluded in a timely manner.
So they weren't just letting the model ramble on.
Right. This was particularly important for tasks like math and code, where the reasoning steps are crucial.
So by refining both the metrics and the prompts, they were aiming for a much more accurate picture of the model's abilities.
Absolutely. And they even developed their own offline inference framework called Flood for large-scale evaluations.
We touched on that briefly. It allows for very consistent results across different setups, right?
That's right. And the fact that they linked evaluation results back to the training data is a really powerful feedback mechanism.
Definitely helps to pinpoint what's working and what's not.
It does. And all these efforts in efficient training and thorough evaluation culminated in the release of Ling Lite and Ling Plus on Hugging Face.
Making their work accessible to the wider AI community.
Exactly. And their findings, especially around the cost savings of training on less powerful hardware, have some really significant implications.
It really does suggest a more democratized future for large-scale AI development.
It does. And the architectural innovations like the fine-grained and shared experts, along with Normhead, offer valuable insights for future MOE model design.
Absolutely. Plus, the techniques they developed for handling training instabilities are incredibly practical.
They are. It shows that building these massive models isn't just about having the biggest computers. It's about clever engineering and a deep understanding of the process.
Well, this has been a fascinating dive into the Ling technical report and their resource-efficient approach to LLM training.
Agreed. It's really inspiring to see such significant progress being made with a focus on accessibility and innovation.
Definitely gives you a lot to think about regarding the future of AI development.
It does. Thanks for joining us today for this in-depth look.
And thank you for your insightful questions and for keeping us on track. We really appreciate you tuning in.
Until next time, keep exploring the fascinating world of AI.